March 19th, 1943. Kummersdorf Proving Ground, Brandenburg, Germany. The ballistics engineer's hand trembled slightly as he recorded the third test result, a measurement that would fundamentally challenge German understanding of American ammunition design. The 50 caliber projectile weighs 706 grains, more than twice the mass of our standard 13mm round. Through the reinforced observation window of Test Cell 4, Heinrich Müller watched a captured American bullet tear through a mock-up fuel tank filled with water and aviation gasoline. The hydraulic pressure wave that followed defied every calculation his team had made. This was not just another captured round brought home for evaluation. This was evidence of a manufacturing philosophy that German ordnance engineers had never seriously considered, and its implications would prove more devastating to Luftwaffe confidence than any tactical defeat. The kinetic energy concentrated in a single American 50 caliber projectile, when multiplied across 13 gun positions on a B-17G Flying Fortress. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Created a level of structural damage that German fighter pilots could not overcome through skill or courage alone. The transformation from enemy ammunition to intelligence priority had begun 2 months earlier, on December 12, 1942, when Lieutenant Paul Flickinger's B-17F crashed in France. German recovery teams swarmed over the intact bomber, photographing every system before damage or souvenir hunters could compromise the intelligence windfall. But the bullets loaded in the bomber's ammunition boxes drew particular attention from ordnance specialists, who immediately recognized something unprecedented in their construction. 9 defensive gun positions surrounded this B-17F model. Later variants would carry 13. Each position fed from belts containing hundreds of 50 caliber rounds manufactured to specifications that seemed impossible given wartime industrial pressures. The consistency across different manufacturers, the precision of dimensions, the uniform performance of powder charges all indicated American mass production sophistication that German industry had never achieved, despite possessing superior theoretical knowledge. Within hours of the bomber's capture, ammunition boxes were shipped separately to Kummersdorf, the German army proving ground located 25 kilometers south of Berlin in Brandenburg. This secretive facility served as Germany's primary testing center for all captured Allied weapons and equipment. Here, hundreds of technicians, ballistics engineers, metallurgists, and ordnance specialists dedicated themselves to understanding how enemy weapons worked and how to defeat them. For 3 months following the ammunition's arrival in mid-December 1942, teams of specialists conducted exhaustive examination of the 50 caliber cartridge. Engineers measured case dimensions with precision instruments, finding tolerances that seemed impossibly tight for wartime mass production. They analyzed powder composition, discovering propellant formulations that burned more consistently than German equivalents. They tested primer sensitivity across temperature ranges, documenting performance that maintained reliability from Arctic cold to desert heat. Every component received detailed documentation. The brass cartridge case, with its distinctive bottleneck design, revealed American understanding of pressure curves and extraction reliability. The projectile construction showed sophisticated manufacturing using copper jackets formed around steel or incendiary cores, with precision that German ammunition plants rarely achieved. The primer assembly demonstrated quality control that ensured ignition reliability approaching 100%, even under adverse conditions. Luftwaffe ordnance engineers marveled at aspects of American ammunition philosophy revealed in the 50 caliber cartridge. The round demonstrated standardization on a scale German industry had never achieved. Different manufacturers produced ammunition that was completely interchangeable without adjustment or selection. Head stamps from Lake City, Twin Cities, Denver Ordnance, and a dozen other plants showed identical performance, despite being manufactured thousands of miles apart using different tooling and workforces. Where German ammunition required careful lot matching and frequent adjustments to maintain consistency, American 50 caliber rounds performed identically regardless of manufacturing source. Quality control procedures ensured that rounds produced in January performed the same as rounds produced in December. Ammunition manufactured for training purposes could be used interchangeably with combat loads without weapon adjustments. Everything about the ammunition's construction indicated an industrial philosophy fundamentally different from German practice. Where German ordnance required skilled craftsmen to maintain tight tolerances through careful hand inspection, American ammunition used statistical quality control and automated gauging that caught defects before they left the factory. Simplified manufacturing sequences reduced the skill level required for workers, allowing semi-skilled labor to produce precision ammunition. Standardized components meant parts from different suppliers fit together without custom fitting. The implications were staggering for German planners who understood industrial capacity. If captured ammunition showed this level of manufacturing sophistication, suggesting an industrial system optimized for volume production, how much could American factories produce in a month, in a year? The numbers, when German intelligence analysts ran the calculations, suggested production rates that seemed impossible, yet proved conservative. On March 19, 1943, Kummersdorf finally began live-fire ballistic testing of the Fausting 50 caliber ammunition. Heinrich Müller, an experienced ordnance engineer selected for his technical expertise and systematic approach, supervised the initial firing tests. The ammunition performed flawlessly, despite being captured 4 months earlier and stored without climate control, confirming American quality control that German ammunition could not match. The 50 caliber cartridge demonstrated remarkable ballistic performance through careful measurement. The projectile left the muzzle at 2,850 feet per second, substantially faster than German 13mm rounds despite greater mass. Trajectory remained flat to 600 yards, making aiming calculations simpler for gunners under combat stress. Wind drift proved minimal compared to smaller calibers, explaining why American gunners achieved hits at ranges German pilots considered impossible. Over subsequent weeks throughout the spring of 1943, Kummersdorf engineers conducted varied test profiles, designed to explore every aspect of the ammunition's performance characteristics. Penetration tests against armor plate showed the armor-piercing variant could defeat 22mm of hardened steel at 100 yards and 19mm at 500 yards. These figures exceeded German 13mm AP performance, despite the American round's lower sectional density. Incendiary testing revealed sophisticated chemical formulations that ignited reliably even after passing through multiple layers of aircraft structure. The armor-piercing incendiary variant combined penetration capability with fire-starting potential in a single projectile, something German ammunition designers had attempted but never achieved with comparable reliability. Tracer rounds burned brightly from short range to beyond 800 yards, providing visual feedback that helped gunners adjust their aim while simultaneously intimidating attacking pilots. But the tests that would prove most significant to Luftwaffe tactical understanding involved firing into simulated aircraft structures. Understanding how 50 caliber rounds damaged real aircraft became the highest priority for ordnance specialists across all Luftwaffe technical branches. The numbers alone were sobering to German engineers who understood the physics. The 50 caliber armor-piercing round delivered between 10,000 and 15,000 foot-pounds of kinetic energy at the muzzle, depending on the specific loading. This represented 3 to 5 times the energy of German 7.92mm rifle caliber rounds and substantially exceeded even German 13mm heavy machine gun performance. When German test engineers began firing captured 50 caliber ammunition into aircraft structure mock-ups, they discovered damage patterns that explained why American bomber crews placed such confidence in their defensive armament. A single 50 caliber round striking an aircraft wing spar could fracture the metal, compromising structural integrity. Hits on control surfaces, severed cables, and destroyed actuators. Impacts on engine mounts cracked aluminum castings that would require factory replacement. Heinrich Müller supervised the most revealing tests conducted in April 1943, examining what happened when 50 caliber rounds struck fuel tanks. The engineering team constructed realistic fuel tank mock-ups using aluminum sheet metal of varying thicknesses, filled them with water mixed with gasoline to simulate combat fuel loads, and fired single rounds from increasing ranges. What they discovered would revolutionize German understanding of why B-17 seconds proved so difficult to shoot down. When a 50 caliber projectile traveling at 2,800 feet per second struck a fuel tank containing liquid, it created a phenomenon called hydraulic ram that German engineers had never adequately modeled or anticipated. The projectile, entering the fuel tank, transferred its enormous kinetic energy directly into the incompressible liquid inside. This energy propagated as a pressure wave radiating outward from the bullet track at the speed of sound in the liquid, approximately 4,700 feet per second. The pressure wave struck the tank walls milliseconds after projectile entry, generating forces that could split seams, blow out panels, or rupture the entire structure. Müller's test cell recordings documented the violence of hydraulic ram with scientific precision. A single 50 caliber round striking a fuel tank containing 80% liquid and 20% airspace generated peak pressures exceeding 15,000 pounds per square inch along the bullet track. These pressures lasted only milliseconds, but the force was sufficient to deform metal, separate riveted joints, and tear structural members. The test cell's high-speed photography captured what happened in slow motion. The bullet entered through the tank's front wall, leaving an entry hole approximately half an inch in diameter. Inside the tank, the projectile's passage created a temporary cavity as the incompressible liquid was violently displaced. This cavity expanded to several inches diameter as the pressure wave propagated outward, then collapsed back on itself as the liquid rushed to fill the void. The collapsing cavity created additional pressure pulses that reinforced the initial hydraulic shock. These secondary waves could be more destructive than the primary shock because they concentrated energy in unpredictable ways depending on tank geometry and fill level. The result was structural loading that exceeded anything German tank designers had anticipated or tested against. When the projectile reached the tank's rear wall after traversing perhaps 12 to 18 inches of liquid, it struck with remaining velocity still exceeding 2,000 feet per second, but now it was tumbling rather than flying, point first, and it was accompanied by the hydraulic pressure wave whose energy it had generated. The exit wound measured several inches across as the tumbling projectile tore through metal already weakened by hydraulic overpressure from the inside. Then came the most destructive phase. The hydraulic pressure wave, reflecting off the rear wall, created a jet of fuel that blasted back through both entry and exit holes with tremendous force. This fuel jet could extend several feet from the tank, creating an aerosol cloud of atomized gasoline mixed with air in perfect proportions for ignition. Any tracer or incendiary round following the armor-piercing round would find this fuel cloud and ignite it instantly. German engineers testing against lightly constructed fuel tanks similar to those used in Japanese aircraft documented even more catastrophic results. Tanks without substantial structural reinforcement simply exploded when struck by 50 caliber rounds if they contained significant fuel loads. The hydraulic ram literally blew the tanks apart, separating wings from fuselages in some test shots. This explained combat reports from the Pacific Theater describing Japanese aircraft disintegrating when struck by American 50 caliber fire. But American bombers like the B-17 incorporated self-sealing fuel tanks that added another layer of complication to German understanding. The test team at Kummersdorf obtained technical drawings and specifications for American self-sealing tank construction through intelligence sources, and what they learned troubled them deeply. American self-sealing tanks consisted of multiple layers of specialized materials. An outer structural shell of aluminum alloy provided strength and shape. Inside this shell sat a layer of untreated natural rubber approximately 3/8 of an inch thick. Inside that layer sat a layer of vulcanized rubber approximately 1/4 inch thick. The innermost layer consisted of fuel-resistant synthetic rubber that contacted the gasoline directly. When a projectile pierced all these layers, the damage sequence followed a carefully engineered pattern. The hole in the outer structure allowed fuel to seep into the untreated rubber layer. This rubber, specially formulated to absorb petroleum products, began swelling immediately upon contact with gasoline. As it swelled, it gradually closed the hole, reducing and eventually stopping fuel loss. The system worked reliably against rifle-caliber rounds that created holes small enough for the swelling rubber to seal completely. German 7.92mm rounds typically created holes less than 8mm in diameter that the self-sealing material could close within minutes. Even German 13mm rounds created holes that, while larger, could be substantially reduced if not completely sealed. But the 50 caliber round created holes that challenged the self-sealing system's capacity. The half-inch entry hole and the much larger exit wound allowed substantial fuel loss before the rubber could swell enough to reduce leakage. More critically, the hydraulic ram generated by the 50 caliber's kinetic energy could separate the rubber layers from the aluminum structure or tear the rubber itself, creating failures the self-sealing material could not repair. Müller's team documented this in careful tests, firing into replica self-sealing tanks constructed to American specifications. Against tanks filled to 80% capacity, 50 caliber armor-piercing rounds created immediate leaks that the self-sealing material could reduce but not eliminate. The exit wound proved particularly troublesome, with the hydraulic jet blowing fuel out faster than the rubber could swell to close the hole. Worse, the hydraulic ram could cause structural damage beyond the immediate penetration. The pressure wave propagating through the fuel-cracked aluminum baffles separated fuel bladders from mounting points and split seams between panels. Even when the self-sealing material functioned as designed, closing the bullet holes within minutes, the structural damage from hydraulic ram left the tank compromised and leaking from seams and joints. This explained why American bombers could absorb tremendous punishment and continue flying. The self-sealing tanks reduced what would have been catastrophic fuel loss to manageable leakage. But the 50 caliber round's kinetic energy was so great that even with self-sealing tanks, American bombers could not shrug off hits completely. They simply survived long enough to reach friendly territory where they could make emergency landings. German engineers examining captured B-17 components discovered another unsettling aspect of American ammunition effectiveness. The Americans loaded their 50 caliber belts with carefully chosen ammunition mixes that maximized different effects. A typical American bomber ammunition belt contained approximately 25% armor-piercing rounds for penetrating structure and reaching vital components. 25% of the belt consisted of armor-piercing incendiary rounds that combined penetration with fire-starting capability. 20% consisted of tracer rounds that helped gunners see where their fire was going. The remaining 30% consisted of ball or incendiary rounds optimized for different target effects. This mix meant German fighters attacking B-17 seconds faced varied threats from every burst. Armor-piercing rounds punched through engine cowlings, penetrated armor plate, severed control cables, and destroyed equipment. Incendiary rounds started fires in fuel systems, hydraulic lines, electrical wiring, and anywhere flammable materials existed. Tracers provided aiming references while creating psychological effects on pilots who watched golf ball-sized projectiles flash past their canopies. The mixed loading also meant German pilots never knew which round would strike their aircraft next. An armor-piercing round might pass through thin fuselage skin without exploding, causing limited damage. But the next round might be incendiary, setting fire to fuel or hydraulic fluid. The uncertainty created constant psychological pressure on attacking pilots who had to close within 600 yards to have reasonable hit probability with their own weapons while facing this mixed defensive fire. Kummersdorf engineers calculated that a single 50 caliber gun firing 750 rounds per minute threw 125 projectiles downrange every 10 seconds. Each projectile carried enough kinetic energy to destroy any aircraft component it struck directly. The probability of lethal hits increased dramatically at closer ranges, where accuracy improved and kinetic energy remained highest. When German test pilots learned these ballistic statistics through intelligence briefings, the numbers shaped tactical decisions across all fighter units facing American bombers. Attacking from behind meant flying directly into the most concentrated defensive fire zone, where tail gunners, dorsal gunners, and waist gunners could all engage simultaneously. A fighter pilot boring in from 6 o'clock faced at least 4 and sometimes 6 heavy machine guns concentrating fire along his approach corridor. Attacking from below offered no better prospects after examining the ball turret's capabilities. This remarkable piece of American engineering positioned a gunner in a rotating sphere equipped with two 50 caliber guns that could track targets through 360 degrees of azimuth and from horizontal to nearly straight down. No angle of approach from below escaped coverage. Side attacks faced the waist gunners who, despite their uncomfortable working conditions at temperatures far below zero. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Manned, flexible 50 caliber guns that could engage targets across wide traverse angles. The interlocking fields of fire meant multiple guns engaged a target approaching from beam angles, concentrating fire that dramatically increased hit probability. The tactic that offered the best survival probability involved frontal attacks from 12 o'clock high, approaching from above and ahead of the bomber. Early B-17 models mounted limited forward-facing guns operated by bombardier and navigator, who had other primary duties. But even this approach required exceptional nerve because fighter and bomber closed at combined speeds exceeding 500 miles per hour, giving the pilot perhaps 2 seconds to aim, fire, and break away before collision became inevitable. German intelligence learned that American factories produced approximately 3 billion rounds of 50 caliber ammunition during the war years, from 1942 through 1945. This staggering figure represented more ammunition than Germany produced across all calibers combined for all weapons systems. Peak production exceeded 100 million rounds monthly, more than Germany could manufacture in 6 months of maximum effort. Every factory producing 50 caliber ammunition maintained identical specifications, despite being scattered across the United States from coast to coast. Quality control procedures ensured that ammunition from Lake City Army Ammunition Plant in Missouri performed identically to ammunition from Twin Cities Ordnance Plant in Minnesota or Denver Ordnance Plant in Colorado. This standardization, routine in American industry, remained largely theoretical in German ammunition production, where each plant introduced subtle variations. Additional captured B-17 seconds arrived at German testing facilities through 1943 and 44, each bomber carrying its own load of 50 caliber ammunition that reinforced Kummersdorf's findings. Engineers examined ammunition from different manufacturing dates, different plants, different production lots. The consistency proved remarkable and disturbing. American quality control maintained the same specifications regardless of when or where ammunition was manufactured. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated through Luftwaffe technical branches. These documents, intended for senior officers and armament ministry officials, painted a sobering picture of comparative capabilities. The 50 caliber cartridge demonstrated American industrial maturity that Germany fundamentally lacked despite possessing superior theoretical knowledge. Mass production techniques allowed volume production that overwhelmed German capacity while maintaining quality that exceeded German standards. Interchangeable ammunition from multiple manufacturers eliminated logistical complications that plagued German forces. The entire design philosophy prioritized keeping guns firing rather than achieving theoretical performance maximums that looked impressive but couldn't be sustained in combat. Internal German assessments documented observations that went beyond simple ballistics. American 50 caliber ammunition reflected decades of civilian industry experience that Germany had never developed at comparable scale. Before the war, American commercial shooting sports and hunting industries had created enormous demand for quality ammunition at reasonable prices. This competitive civilian market drove innovations in manufacturing efficiency and quality control that transferred directly to military production. German ammunition industry had focused primarily on military contracts with limited civilian production. Quality control emphasized batch testing and inspection by skilled workers rather than statistical process control and automated gauging. This approach worked adequately for limited production, but could not scale to wartime requirements without sacrificing quality. The comparison became impossible to ignore as field reports accumulated through late 1943 and early 44. American ammunition maintained consistent performance across millions of rounds fired in combat conditions, ranging from Arctic cold to desert heat. Failure rates remained negligible. Malfunctions caused by ammunition defects occurred rarely enough that maintenance records barely documented them. German ammunition, by contrast, showed increasing quality problems as the war continued. Slave labor employed under harsh conditions in ammunition plants introduced deliberate sabotage through subtle defects difficult to detect. Allied bombing disrupted supply chains for critical materials. Quality control degraded as experienced workers were conscripted for military service and replaced by unskilled laborers. By 1944, the pattern had become undeniable to any objective observer examining the evidence. American .50 caliber ammunition demonstrated industrial superiority expressed through consistent manufacturing quality, reliable battlefield performance, and production volume that overwhelmed German capacity. Understanding the enemy's ammunition didn't eliminate its effectiveness, and German fighter pilots had to press attacks home despite knowing each B-17 carried thousands of rounds that could destroy their aircraft. Field reports from Luftwaffe fighter units reinforced the Kummersdorf findings with real-world operational experience. German pilots who survived multiple combats against American bomber formations frequently commented on the effectiveness of .50 caliber defensive fire in letters, reports, and interrogations. They described the psychological impact of watching walls of tracers converge on their aircraft. They detailed the damage single hits could inflict on their fighters. They acknowledged that even successful attacks that destroyed bombers often left the attacking fighter so badly damaged that reaching base became uncertain. The .50 caliber's effectiveness derived not from revolutionary technology, but from mature engineering applied through sophisticated manufacturing. The ammunition used conventional materials and established designs. Nothing about the cartridge's construction violated known physical principles or required scientific breakthroughs. German engineers examining the ammunition found no secrets to copy or innovations to exploit. What they found instead proved more troubling. The .50 caliber cartridge represented American industrial civilization at peak efficiency. Every dimension reflected careful optimization for mass production. Every component showed design features that simplified manufacturing while ensuring reliability. Every specification balanced performance against production capability to maximize total combat effectiveness. Kummersdorf engineers dismantled hundreds of .50 caliber cartridges, studying every component with the thoroughness that would impress any technical investigator. They found much to admire and little to criticize from a purely engineering perspective. The ammunition represented mature design executed with manufacturing excellence that integrated best available technologies into reliable cartridges that performed predictably under all combat conditions. No amount of tactical innovation could compensate for such fundamental disparity in ammunition quality and production volume. Hans-Werner Lerche, who would become the most experienced test pilot flying captured Allied aircraft during the war, flew extensively in captured B-17 seconds and examined their ammunition systems in detail. His post-war memoir, published decades later, acknowledged that American .50 caliber ammunition effectiveness stemmed from industrial advantages German factories could never match. He flew the captured B-17F, nicknamed Wolfhound, during spring and summer 1943, operating its defensive guns during simulated attack exercises. The guns functioned flawlessly throughout hundreds of test firings despite using captured ammunition stored for months, without climate control. Feed mechanisms never jammed. Firing circuits never failed. The ammunition performed exactly as designed every time triggers were pressed. German fighter pilots who flew against American bomber formations developed deep respect for .50 caliber defensive fire based on painful experience. They described approaching the bombers as flying into storms of tracers that filled the sky. They acknowledged that even veteran pilots with hundreds of combat hours sometimes broke off attacks prematurely rather than face the psychological pressure of watching those golf ball-sized projectiles flash past their canopies. Those pilots who maintained formation discipline and pressed attacks home despite defensive fire faced brutal arithmetic. German studies using combat data determined that .50 caliber hits could destroy fighters through multiple mechanisms. Direct hits on the engine could break crankshafts, shatter cylinders, sever fuel lines, or destroy ignition systems. Hits on the cockpit could kill pilots directly or damage flight controls. Hits on wings could sever control cables, puncture fuel tanks, or compromise structural integrity. The damage was cumulative and unpredictable. A fighter might absorb several hits with minimal immediate effect, then suddenly lose power or controllability when the next round severed a critical component. German pilots never knew whether the next 50 caliber round would pass harmlessly through sheet metal or strike something vital that would force them to bail out or make emergency landings. By mid-1944, German technical intelligence services understood that American 50 caliber ammunition represented one component of a comprehensive weapons system designed to project strategic bombing capability deep into enemy territory despite determined opposition. The ammunition combined with the Browning M2 machine gun to create defensive installations that, when multiplied across 13 positions on a B-17G, generated concentrated fire that fundamentally changed aerial warfare. The story of captured 50 caliber ammunition in German hands represents far more than simple ordnance analysis. These cartridges, manufactured in American factories by American workers, loaded into American bombers, captured by German forces, then tested by German engineers, served as windows into Allied industrial capabilities and American manufacturing philosophy. They revealed quality that German ammunition plants could not match despite possessing equivalent technical knowledge. They demonstrated production volumes that exceeded German capacity by factors of 10 or more. They proved American ability to maintain specifications across multiple manufacturers, spread across an entire continent. They showed industrial maturity developed through decades of competitive civilian markets that Germany had never cultivated. Yet ultimately they also demonstrated the impossibility of Germany's strategic position by revealing the scale of American industrial mobilization. Every hour German engineers spent testing captured American ammunition represented skilled labor diverted from developing German weapons. Every test firing consumed time and resources Germany couldn't spare. Every comprehensive report documenting American ammunition superiority underscored industrial disparities that tactical skill could never overcome. Meanwhile, American factories produced more 50 caliber ammunition every single day, replacing combat expenditures faster than German fighters could force bombers to use it. Lake City Army Ammunition Plant alone could produce more 50 caliber rounds in 1 week than all German ammunition plants combined could manufacture in a month. The production statistics remain staggering 8 decades after the war's conclusion. American factories manufactured approximately 3 billion rounds of 50 caliber ammunition between 1942 and 1945. Each cartridge was a complex assembly containing precisely manufactured components: drawn brass case, carefully formulated propellant, sensitive primer, precision projectile with copper jacket formed around steel or incendiary core. Germany never produced even 1 billion rounds of ammunition across all calibers combined during the entire war, despite starting with more advanced ammunition industry in the 1930s. The reasons extended beyond simple industrial capacity. American strategic doctrine prioritized sustained fire from reliable weapons over precision-aimed shots from specialized guns. American geography protected factories from enemy bombing that disrupted German production. American engineering education produced thousands of skilled quality control specialists, while Germany struggled with manpower shortages as casualties mounted. Most fundamentally, American political and economic systems proved more adaptable to total war mobilization than rigid Nazi hierarchy with its competing power centers and ideological constraints. All these factors combined to create the ammunition production advantage that determined outcomes. The 50 caliber cartridge represented just one weapons component in America's vast arsenal, but it symbolized the entire apparatus of American war production. When Luftwaffe officers examined captured ammunition at Kummersdorf, studying its construction, testing its performance, analyzing its ballistics, they were really studying American industrial civilization and its capacity for sustained production. What they learned should have been obvious from the beginning to anyone who studied American industrial capacity objectively. You cannot defeat an enemy who produces ammunition faster than you can fire it, who maintains quality that exceeds your standards despite volume production, who delivers consistent performance regardless of manufacturing source or production date. The ballistic performance that impressed German test engineers was merely visible manifestation of deeper American advantages in industrial organization, quality control methodology, and manufacturing scale. The real weapon wasn't the 50 caliber cartridge's kinetic energy. It was the economic and industrial system that could design, manufacture, and deliver 3 billion rounds while simultaneously producing everything else needed to fight a global war. No amount of tactical brilliance, engineering expertise, or individual courage could overcome such overwhelming disparity in ammunition production. No wonder Heinrich Müller, after testing hundreds of captured 50 caliber rounds and seeing firsthand the quality and consistency of American ammunition, he concluded that Germany had already lost the industrial war by 1943 based purely on ammunition production mathematics alone. The captured ammunition at Kummersdorf answered tactical questions about ballistic performance and damage mechanisms. It revealed vulnerabilities in self-sealing tank design that skilled pilots could exploit. It demonstrated why B-17 seconds could absorb tremendous punishment and continue flying toward targets. But it couldn't answer the fundamental strategic question that determined outcomes. How do you stop bombers when the enemy produces ammunition faster than you can force them to expend it? These questions had no satisfactory answers within framework of Nazi Germany's war strategy and industrial organization. The regime had started a war of conquest, assuming quick victory before enemies could fully mobilize their economies. When that fundamental assumption proved false, when the war became a grinding contest of industrial production and staying power, Germany's fate was sealed by decisions made in the 1930s that created industrial systems incapable of matching Allied production. The 50 caliber cartridge, with its precisely manufactured components, demonstrating American quality control, and its enormous kinetic energy, creating hydraulic ram that destroyed aircraft structures, represented not just tactical ammunition, but strategic verdict on the war's outcome. The ammunition came in endless supply from factories the Luftwaffe could never reach. The quality never faltered despite volume production. The performance remained consistent regardless of conditions. German engineers at Kummersdorf tested captured 50 caliber ammunition exhaustively and documented American manufacturing superiority with scientific rigor. They admired the ammunition's consistent performance that allowed reliable defensive fire. They appreciated its thoughtful design that balanced effectiveness against production capability. They acknowledged its devastating effects when striking aircraft structure or fuel systems. But understanding the ammunition's capabilities did nothing to change the outcome of battles in the sky over Europe. Knowledge of the enemy's ammunition couldn't create the industrial capacity needed to match American production when that capacity simply didn't exist in sufficient scale. By late 1944, many captured 50 caliber rounds in German possession had been expended in testing or rendered unusable through deterioration as storage conditions worsened. But their intelligence value had been exhausted long before. The Luftwaffe knew everything worth knowing about American 50 caliber ammunition through years of study and combat experience. They understood its ballistic performance across all engagement ranges. They knew its damage mechanisms against various aircraft structures. They had developed tactics to minimize exposure to defensive fire. Yet this hard-won knowledge proved increasingly useless against thousand-bomber raids escorted by hundreds of fighters that overwhelmed defenses through sheer numbers. Individual German pilots continued achieving remarkable success against individual bombers throughout the war. Some aces shot down dozens using perfected attack techniques learned partly from understanding 50 caliber capabilities. But heroic individual performance couldn't compensate for systematic industrial inferiority and numerical disadvantage that grew worse each month. For every ace who survived long enough to develop expertise, 10 novice pilots died before learning effective tactics. Average life expectancy for German day fighter pilots by 1944 measured in weeks rather than months. Many never achieved 10 combat missions before being killed or wounded, creating downward spirals of declining experience levels across all fighter units. The Americans, meanwhile, rotated crews home after 25 missions initially, later increased to 35 as loss rates declined. Survivors returned to training commands where they passed combat experience to new crews, creating institutional learning that preserved lessons purchased with blood. Different philosophies reflected different industrial realities. America could afford to rotate experienced crews because production provided steady streams of replacement aircraft and new crews. Germany couldn't spare anyone with combat experience because production couldn't replace losses. Captured .50 caliber ammunition taught the Luftwaffe much about American ballistic engineering through systematic testing. The experience of fighting against bomber formations, carrying millions of rounds, taught harder lessons about American resolve, resources, and industrial staying power. But the ultimate lesson came in May 1945, when guns fell silent across Europe. Germany lay in ruins, its cities destroyed, its industry shattered, its military crushed between Soviet forces in the east and Allied armies in the west. The bombers had done their work over years of sustained operations. The ammunition that impressed German test engineers in 1943 had proved sufficient for B-17 seconds and B-24 seconds to complete their mission, despite taking terrible losses, with thousands of bombers destroyed by German fighters and flak. The story ends where it began, in the sky over Europe, where men fought and died in machines that fired ammunition representing their nation's industrial capabilities and approaches to warfare. Heinrich Müller survived the war and continued working in ammunition development during Reconstruction. He remained proud of his technical work while acknowledging the futility of trying to match American production scale with German resources. His expertise testing captured ammunition made him valuable to Allied technical intelligence after the war, and he contributed to several projects evaluating German and captured Allied ammunition for post-war applications. The .50 caliber ammunition he had tested so carefully in 1943 continued serving in American military forces through Korea, Vietnam, and into the 21st century, testament to the design's fundamental soundness. Wolfhound, the first intact B-17 captured by the Luftwaffe, carried approximately 7,000 rounds of .50 caliber ammunition when it landed in France in December 1942. During its service with German forces from December 1942 until destruction in April 1945, it taught German aviators and engineers volumes about American ammunition, gun systems, and defensive tactics. The lessons proved intellectually valuable but strategically irrelevant to changing outcomes. Understanding your enemy's ammunition doesn't eliminate its effectiveness or create counters when resources don't exist. The .50 caliber rounds that German engineers studied so carefully represented American industrial philosophy made tangible in brass and lead. Overwhelming effectiveness through volume of fire, consistency through statistical quality control, reliability through mature manufacturing, all designed to ensure defensive guns kept firing throughout missions. This philosophy worked despite heavy costs, despite losing thousands of bombers, despite casualty rates exceeding 20% in some units during 1943, despite German fighter opposition that destroyed hundreds of aircraft in determined resistance, the strategic bombing campaign succeeded in its objectives. Germany's war industries were destroyed, its cities burned, its transportation networks collapsed. And when the war ended, American factories were still producing .50 caliber ammunition at rates that would have allowed complete replacement of all combat losses within months, demonstrating ultimate futility of fighting an attrition war against American industrial capacity. The captured ammunition in German hands became unwitting evidence of their own nation's defeat. Every test firing revealed American quality. Every ballistic measurement documented American advantages. Every technical report emphasized the same inescapable message. America possessed ammunition production capacity that Germany could never match through any realistic means. The ballistic performance was impressive and merited technical respect. The production capacity behind it was overwhelming and ultimately decisive. That was the real lesson of the captured .50 caliber ammunition, though it took time for all participants to fully comprehend the implications. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.